Okay, section 5.7. Now that we know the simplex algorithm is an iterative algorithm, we need to discuss convergence. Any iterative algorithm, that's something you should do. So the simplex algorithm is a theorem that can be proven that it converges. There's only two things that can happen. It either converges to an optimum in a finite number of steps, provided lambda is greater than 0 at every step. So what is that really getting at? Lambda greater than 0. Now that we had the last section, we know that's saying it's non-degenerate. It's never going to encounter degeneracy along the way. If that's the case, then it can converge in a finite number of steps. And we'll talk about what finite means in a moment. Or it could stop and say the LP is unbounded. That would be if it ever encounters a lambda equals infinity at any point. Okay, now why do we say finite number of steps? And can we be a little more specific about that? Well, at every iteration, a new basis is obtained. And that means there's one leaving variable, one entering variable. Those each correspond to a column. So your A matrix, the submatrix that you pull off, and later we'll actually call that submatrix out of A, we'll call that B for basis. And so that B matrix changes, one column leaves and another one comes in. So I have an entering column and a leaving column. If in general, we talk about an M by N A matrix, there are M constraints and N variables. Again, we want to pull off M of those columns and make an M by M matrix that is a basis, linearly independent, spans the space. For that general case, then the simplex basis chooses M columns from that N possible, that should be N here, N possible. And so really the maximum number of bases that could be formed is N choose M, which that's our N factorial or M factorial, and when it's M factorial. Okay, that's finite, but it could be really, really large. And so of course that's a worst case analysis because we're saying out of the maximum possible. So you could have an N choose M. But in practice, simplex actually takes much, much less. And so let me just give you a couple more specifics here. There's a famous counterexample called the Clementi. Maybe the 70s or 80s, someone came up with an example that showed, it was a contrived example, small, maybe N equals 8 or 10 or something, example that showed that simplex actually had a worst case exponential behavior, right? So that's terrible. Worst case exponential behavior. But again, that was totally contrived, hard to find. In practice, what actually happens, so more the average case is what you usually describe, it actually shows linear behavior. It's amazingly fast, amazingly simple to code, you're gonna see that, and super efficient. So linear algorithms, hard to beat that, right? So, and we'll talk a little bit in a moment about big O notation if you haven't seen that. But let's come back to this finite. Let's think of an example. So like a medium-sized LP these days would be maybe A is 10,000 constraints by, let's say, 50,000 variables. Again, that's a mid-size. Well, what is 50,000 choose 10,000? So I tried to get MATLAB to do that. MATLAB, it gives out not a number, it's bigger than the largest number that MATLAB would store. So the largest number MATLAB stores is this. They're not a number, and MATLAB is about 1.79 times 10 to the 300, right? 10 to the 300 power, very large, right? It's still finite. So we could say that this theorem holds, yes, but in practice, like that seems like really bad news. But again, that's a worst case analysis. What's actually happening in practice is it's so much better that it's linear. Okay, so that's the convergence analysis we're gonna do. We'll come back and talk a little bit more, but the good news is you can prove it converges with this caveat that there is no degeneracy. Now, the second thing we need to talk about here is cycling. So let me make some room on the board. Okay, let's quickly talk about cycling. So if lambda equals 0, you have at least one degenerate basic feasible solution that simplex could cycle, which is just a way of saying that it could encounter the same basis again. And sometimes you could do it in such a way that you're sort of looping around that same basis. You never really, you don't have a rule or a mechanism for choosing, making sure you've exhaustively gone through all those same bases. And maybe you're just, there's a way in which you've picked like a representation basic feasible solution A, and then there's a representation B, C, and then you come back to A again. And so you need a way that goes through all of them. Maybe there were F of them. And then once it's done that, at least one of those will get you out of there. And so you can get cycling or looping. And so let's go to page 259, table 5.8. Okay, this table is an example of cycling with the simplex. And so this is actually a small example. And in fact, it's famous because it was so hard to find an example of cycling for a small problem. And so folks did. And again, you can see the C, the A, this is the way we usually write our simplex. Here's our change vector, the minimum ratio test, the next iterate, who's basic, who's non-basic, and so on. And what happens is that we actually come back to the solution that we've seen before. So x0 and x6 are identical. And again, there's the statement, cycling is actually quite rare. And so there are anti-cycling rules though, and there's usually something called like lexicographic ordering, the way in which you're going to go through those basic feasible solutions that are actually the same, that correspond to the same BFS, those bases, sorry, the bases that correspond to the same BFS. I should have said bases A before, right? Bases B, bases C. They keep bringing you back to the same basic feasible solution. There are mechanisms to go through those in a particular order. Usually there's something called lexicographical ordering. Those anti-cycling rules though, however, because cycling is just so rare, it's usually not worth the effort to implement it. And so most production code, actually the default is to not implement anti-cycling, but if you happen to encounter one for your, typically it's going to be a research problem, less a problem for a client. But if you did encounter cycling and you're like, this is a possibility, what might be happening. I know it's degenerate, I've seen some lambda equals 0 steps. Let me implement anti-cycling. Just search in the help on that particular software program and you'll probably find that there do exist anti-cycling rules. So we just turn that option on. Okay, one last thing for this section. Okay, we're going to talk about big O notation. I find most semesters students haven't seen it or maybe just barely saw it in a little computer science class, a little bit of big O notation. And so when we were saying that the simplex actually has worst case exponential behavior, we could use the notation like this, big O to the n. And this is a way of classifying different algorithms. These are bad algorithms down here that are exponential. There's some parameter in the model, n for us is the number of variables, or we could also relate it to m, the number of constraints. But in general, we'll stick with just one of those. This is a very loose way of categorizing algorithms. And they get better as they go down. This would be linear. It's linear in the number of variables. And we said on average, in practice, simplex is linear. That's fantastic. It's hard to find a linear algorithm that does what simplex does. You know, it isn't a trivial thing. It solves meaningful problems in linear in practice. That's part of the reason it is one of the greatest algorithms of the last century. And so let me just show you a little bit about this big O notation by way of examples of things that you've seen before. So you guys have seen, having had linear algebra and calculus 3, a dot product, right? So, and we do this a lot, right? We do C dotted with X in linear programs, right? And each of these are a vector. And another way of writing it is C transpose X. This is really like a row vector times a column vector, right? And you do C1 times X1 plus C2 times X2 plus and so on, so on, so on. And how many scalar multiplications are you doing in that? Well, there are n things in this. This is a 1 by n by an n by 1. So you're really doing n scalar multiplications and additions. So in total, this is called ON work. So again, roughly, you don't need to actually say there were exactly this many scalar multiplications, exactly this many additions. We know exactly there would be what, n scalar multiplications and n additions, or n minus 1 addition. Maybe. But on the order is big O of n. That's a linear operation to do that. That's much easier than say, what if you do a matrix times a vector, like we do AX in this class. Let's just keep things simple. This is say n by n and n by 1. Well, what is the work here? When you do this, you're going to get an n by 1 vector. Well, the first component in this vector is achieved by actually doing an inner product, right? A dot product. The first row in that column that we already determined from above was ON work. So we have ON work here, ON work here, dot, 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 ON work for each dot product or inner product. So for a total of n things. So that's how you get to ON squared work. So this is a dot product or vector-vector multiplication. Let's just write like this. Vector-vector multiplication. This is matrix vector multiplication or vector matrix, if you did it on the left side. So what is an example of ON cubed? That would be like a matrix times a matrix, A times B. Again, let's just keep it simple, say above square. How do you get the first component here? The 1, 1 component is this row and this column. That is an inner product, a dot product, which is ON work. So we actually have n squared elements times ON work, which is ON cubed. Right, so we're increasing in work as we go down these classic operations in linear algebra, matrix multiplication. And again, exponential, this is way worse, terrible. And just to show you how important it is to reduce this, so there's actually some in between, like if you can take an algorithm that was n squared by sophisticated storage procedure or subroutine, make it say something a little less like n log n. That lives in between these two. That would be a major accomplishment to speed up the algorithm. And so there's all different levels in between these that can be achieved. And again, another way of thinking about how important this is, a matrix multiplication, that's a fundamental operation in many routines, many algorithms. We're going to do that. You'll see some in the simplex. We'll see, or inverse, that's another ON cubed. So the inverse operation, inverse of a matrix, what else? RREF, those are ON cubed, Gaussian elimination, all ON cubed. Sometimes Gaussian elimination is like n cubed over 3, but again, on the order, you don't care about that constant in front. It's just really an n cubed algorithm. Again, fundamental in many algorithms is matrix multiplication. And folks have been trying to do smarter, more efficient storage or subroutines or procedures that could lower this cube by some small amount. And I think they've gotten down to something like this. This is something I'm remembering from graduate school, so I don't know the numbers exactly, but like it was 2.712. There are fancy ways of manipulating the standard matrix multiplication algorithm that you learned. That's really what computers are coding, but maybe there's something more sophisticated you can do for certain types of problems. Maybe they have structure and you can multiply them faster. But there was a woman at NC State, I did my graduate work there, who had spent 20 years trying to chip off a few little fractional points off of that. And folks have, again, gotten down to like 2.8, and maybe the next best one. But if you could do that, you'd be a millionaire, because that's code that you could market in so many production things are built on matrix multiplication. If you suddenly came up with a way to do that faster, it doesn't seem like much going from here to here, that'd be huge savings when you're doing that, repeatedly, iteratively, over and over again. anyways, Carla Savage eventually she had spent 20 years and then moved on to other research and gave up. That's as far as she could get it down, her and her colleagues. Okay, so again, summary here is that simplex, that's about as good as it gets. Oh, of course, there's other ones like, what are you doing? That would be a square root of n. Probably isn't much meaningful, but that's the average case of simplex. This is the worst case of simplex, but those are contrived counterexamples that are hard to come up with. All right, so think about that while you're doing your MATLAB code for the simplex. Are there any ways in which you could save storage? Are there ways in which you could do an operation more efficiently? Maybe not running on the whole, like you're doing this a good bit and then MATLAB code, a delta x equals 0, but there's a couple components in there that maybe because the non-basics are set to 0, so maybe you don't need to find those components. Shifting things around, could you maybe save something and repeat, if it's just slightly different from one iteration to the next, save that and use it in the next iteration. Saving work, those are bells and whistles for your code. You just have to do the simple simplex, but if you like it, enjoy it, there's lots of things you could do to improve it.